All right, let's get started. Sorry for that delay, guys, folks. So, as you know, assignments D1 and D2 are kind of that paired assignment, and they're technically still due on Sunday, but I extended their grace period until Wednesday night, technically Thursday at 10 a.m. So if you turn it in any time between now and Thursday at 10 a.m., no penalty. Today's lecture, I think, will be helpful because we're actually going to talk about assignment D2. And so you've had a good chance to practice with it. And then now hopefully this will answer some of your questions. So everybody is sort of well suited going into it. I heard some good discussions as I was walking in. I think all the right questions were being asked and all the right answers were given. So I think that's great to hear. Okay, so let's move on here and see what we've got. So this assignment that, get rid of that toast up there. All right, so that this assignment was focused on this idea of the tank of a toilet as a very simple example of a physically embodied negative feedback system or a balancing feedback system. So the idea here is we have some water level that's attempted to be balanced. And so whenever it is far away from its target, then there is an action in the system which tries to bring it back to its target. And so there is a gap which represents the how far it is from where we want it to be. And there is a device in the system which monitors that gap and causes the water level to rise. So if the gap is large, the water level will rise. But as the water level rises, the gap will be smaller. So eventually, as the water level becomes equal to the target water level, the gap will go to zero and the water level will stop increasing. So that's kind of the basic idea behind this. Now, we have to say, well, there's a critical component that's missing in this causal loop diagram, and that's that actual device which is controlling the flow of water. So it's the valve that controls that flow of water here. So you could go to a hardware store and buy such a valve. It has such a float device on it, which effectively measures this tank gap, and then based on the position of this float, changes the amount of water coming into the tank. So we're going to put that flow of water directly into that causal loop diagram. And this kind of gives us a better idea of the real dynamics of this system. And so if the water level is well under the target water level, the gap is large. If the gap is large, the flow from the valve is large. If the flow from the valve is large, the water level will quickly rise. But then that will reduce the gap, which will reduce the flow, which will reduce the rise in the water until eventually the water level settles down at some point, hopefully close to, if not exactly at, our target water level. So that's the system here, and that's what I mean. This is a very simple example of a negative feedback system, of a balancing feedback loop that you can see in everyday life. So, what would this look like if we simulated it? Well, what we're going to start talking about today is how to use Vensim to draw a diagram like this one, which will actually simulate this stock, the water level, and this flow, the flow of water, so that you don't have to use spreadsheets to do this sort of thing. So it's maybe a much more intuitive way to go from a conceptual understanding of the system here to a truly dynamic realization of the system that we can simulate over here. But in order for us to understand how to do that, then we need to understand like what this like DT thing is and a little bit of what's going on behind the scenes, which is why I've been torturing you with this spreadsheet stuff for the short period of time. So the critical variables here are, like I said, the stock is the water level. Stocks are things that are changing over time. We've got the flow, which is, this is the thing that's causing the stocks to change. That's what they're called, flows, otherwise called rates. And then we've got these convenient things here just to clean up the diagrams: target water level and tank gap, which I've drawn here as these circles: target water level and tank gap. And then the other things we have on here are all the things connecting those things together, the links. So those are our informational links or causal links, which show how all these things are interrelated. So if I were to drill down into this diagram or drill down into your spreadsheets, I would see formulas like this. Somewhere I would see that this target water level is just got 15 in it. I'd see that this tank gap has got target water level minus water level, or if you didn't have a separate target water level converter, it might just say 15 minus water level inside there. And then if I looked into the flow, which is the thing that's controlling the change of this stock, it would just have the tank gap. Or if you didn't define a separate tank gap converter, you could compress all of this formula into the flow. So this flow is just going to have 15 minus level in it. And so, so hopefully this is feeling familiar in the sort of the things you've experimented with the spreadsheet, so we can kind of see how the spreadsheet sort of stuff is going to translate into this, where this will end up doing all the tedious filling down and all of those sort of things for us. So the other things we have to worry about whenever we have a stock and flow is not only the formula that goes into the flow, but also the initial condition of the water level. We are simulating the toilet after it's been flushed, so the water level is at the bottom of the tank, so it has a water level of 0. So inside here, there's going to be initial condition equal to 0. And then the other thing that's hidden on this diagram is that time step dt. And so I might say that dt is 0.01. I might have to play around with it to figure out what's the best dt. Smaller is always more accurate, but once you get certain, small enough, you don't have to go any smaller, and it'll keep your simulation from running a really long amount of time. So that's kind of captures all of the dynamics that go into the stock and flow diagram. Now, we haven't learned how to draw this in Vensim yet, so we're currently limited to using a spreadsheet. And so this is assignment D2. And so I know people emailed me and I said, well, where do I use W in assignment D2? There is no W. W is and this is a common question, so several people asked this. W was our waiting time between bacterial reproduction events. And I just called it W for waiting time. So W isn't a general property of all models, it's a property of just the bacteria model. Here, the converter of interest is target water level, which I could put up here like a T value, or I could spell it all out, target water level up here. So this is similar to your bacterial case, where you've got a DT defined and some constant, some parameter, some converter defined up here, target water level, which I've defined as 15. Now, you don't need this. You could also just fold that constant, what we call that literal 15, directly into those formulas, but it just makes it more readable to break it out like this. If your solution doesn't do this, that's fine. If you put the 15 directly into your formulas, that's fine. That's no problem. But if you broke it out like this, it just is a little bit more readable. This is a little bit more conventional way to do it. That way, you could change the target water level. You can make it higher or lower, and you don't have to update all your formulas. You just change it in one place. Okay, so that's the first thing. Now, the other thing we have to do that's specific to this system is we have to put in our initial condition. So our initial condition for the stock is 0. And then we have to put in the formula for the flow. Now, this formula is just 15 minus whatever the current water level is. Now, where did I get that formula? I gave it to you. It's almost like I went to Home Depot, I grabbed a flow, I grabbed a valve, I looked at the specifications of the valve, and the valve might tell me that it regulates the flow so that it's whatever gap it measures is going to be the flow in centimeters per second. And so that's where I just look it up. I say, if I'm using this valve is designed so that whatever the current gap is, it takes that gap and it creates a flow equal to the gap exactly. It's not scaled at all. It's exactly that. And that's why I just dump that formula in here, and that will simulate that particular valve. If I had a different valve that had a different relationship between gap and flow, I'd put that relationship here. So these are all the system-specific things. Everything else that I'm about to put here, well, almost, I'm going to move this flow of water in, so maybe I'll do that next year. So the other system-specific thing here is my flow is just a copy of the tank gap. So the tank gap is a converter, which is just here to increase the readability of the model. And then I say the flow, which is the rate of change of the stock, is just exactly equal to the tank gap. And so this is kind of a wasteful column in Excel, because I could have just made the tank gap over here. But this kind of at least allows me to do some other calculations out here, like calculate the tank gap, and then allows me to potentially have a different flow here. So I mentioned I could have gone to Lowe's or Home Depot or whatever and found out that actually they take the tank gap and they cut it in half. And that's how they've designed this one, in which case I would do like 0.5 times D5 instead of just plain old D5. So I don't necessarily have to break these apart, but it just makes it more convenient to break them apart. So these are my system specific things. Before I advance, so I'm going to advance and then I'm going to show you the generic formulas that apply to every single stock and flow diagram. Those ones will not change regardless if we're modeling bacteria or modeling toilets or modeling whatever. But are there any questions about how we got this, how we got from a toilet to here? Let me see, questions online? Okay. So if you set up these sorts of things, you're almost all the way done. Now it really does become like the bacteria model. So the next thing we need to do is populate our time column. And just as in the bacteria column, the time column is always the previous time plus dt. And then we can fill that thing down. The next thing we need to do is populate the other columns. So the water level column, that is just going to be the previous stock plus all of the inflows. You could imagine parentheses around this. All of the inflows minus all of the outflows. In this case, there's only one inflow, the flow of water. So that's why it's just C5 here. So that's the previous water level, B5, plus the flow of water from that row, C5 times dt. Exactly the same as it was in the bacterial case, in the simple bacterial model. So we can take now the flow formula, the tank gap formula, and the water level formula and the time formula, and fill those all the way down. Before I get to that, to see what that looks like, are there any questions about how we got these formulas? And also questions online. Yeah. On the time? So the time always starts at 0, and then the system moves in tiny little steps of 0.01. And so what this is saying here is take the previous time and add 0.01 to it. And then that time in the next one will be that time plus 0.01. That's right. So we're just taking tiny steps, like I'm taking tiny steps in space, but imagine this is taking tiny steps in time, where we assume everything's constant in between those times. Okay. Any other questions? Okay. All right, so what does that look like after we fill it all down? Fill it all down, there's a bunch of numbers here. This, by the way, never include a screenshot of this in like a document. So when we look for your work, when you're turning your assignments, then we'll ask you to submit your Excel spreadsheet, just so if Eric needs to double check how things were done or to sort of investigate some weird things that goes on, then we need to see sort of, the background Excel spreadsheet, just as kind of like for provenance, to understand where everything came from. But your document should be something like you're presenting to a stakeholder, and a stakeholder is not going to make any sense of this. Nobody wants to look at a table of numbers. But graphs, that looks great in your document. So you include this sort of thing in your document. And what we have here, you see a little legend down here at the bottom, is the blue line is the water level in the tank. And I didn't ask for it, but if you want to, you can also plot the red line here, which is the flow of water. And what we see is that the blue line starts at 0, it quickly rises initially, and then it takes a long amount of time to taper off, and it never quite reaches 15. It's like 15 is an asymptote to the system. The red line, the flow of water, if you kind of think about it using your kind of calculus, imagine the slope of this blue line. The slope is really steep here. It gets less steep, less steep, less steep, until the slope is basically 0. This red line, which is the flow, is just the derivative of the blue line. It's the instantaneous slope of that blue line. So you didn't realize it maybe, but what you've effectively done is solved a little differential equation where you gave it the derivative first and it took the integral out. So you said, what if my derivative was 15 minus L? And I want to take, and that's so dl dt is equal to 15 minus L. What this spreadsheet does in the blue line is it says, this is what L looks like over time. if the derivative is 15 minus L. So it's like we started with the red line, and if you took the integral under the red line, you would get the blue line. But we didn't have to do any of the math. The spreadsheet did it all for us. Okay, so so are there questions about this so far? Does this track what some people are getting or not track, and have some questions? So this is the kind of, again, I think I only asked for the blue line. So if you only turned in the blue line, that's totally fine. If you want to include the red line, the flow, that's fine as well. I'm just including it here to make it clear that the flow is really the derivative of the stock. Okay. Okay, so like I was saying, this stock and flow diagram up here is just a graphical version of this mathematical expression down here, where dt, the derivative of water level, so if water level you can call L if it's easier to say here, is equal to the target water level, 15, minus the water level. So I could, like I said, I could go here and I could write in, this is L, and this is 15 minus L. And so that's, and that would, this, the solution to this will end up giving me exactly that. So, so if I solve this equation here using tools, I could go through this, it's not really that important for me to do, but I could in principle go through the process of using calculus-based methods to go from this differential equation to this solution, where the water level at any given time is the target water level times this expression here, 1 minus e to the negative t. I could solve this and get exactly that. And then I could plot this expression here. And I could even take the derivative of water level and plot the expression that I get there. And if I were to plot both of those, I would get exactly the blue line for this expression and the red line for the derivative of this expression with respect to t. So I could do it mathematically, but here I can do it numerically. Now, there are much more complicated systems with lots and lots of stocks that are much harder to do mathematically, analytically, to do this step here. But we can always do them numerically. We can always do them in a spreadsheet or in Vensim, as long as we choose our DT really small. So that's the power of this method. It's not just an alternative way where, like, if we were really kind of had the intestinal fortitude, we could just do the math. Sometimes the math is difficult for even an expert to do. And so I'll tell you, I work with a lot of applied mathematics grad students, and most of them who work with these systems, they're so complicated. This numerics is all they do to solve their problems. They've actually given up on doing the analytics. They had to learn all the analytics to get through their qualifiers and whatever, but then once they get over that, their practical problems are so complex, they don't actually do the math anymore. They just do effectively this up here and use simulations to generate these plots. Okay, so any questions about this process or about the toilet model there? So there was an extra credit on that, which I won't go over, but I definitely encourage you to take a look at, where we add to this an outflow, similar to how we added deaths to the bacterial model. And that outflow is just a constant 1 centimeters per second, if I remember correctly. And then I ask you some questions about, do the outputs that you see here make sense? Does the target water level go to where you'd expect it to go to? So here it levels off at around 15. Does the one with the outflow level off at 15 or level off at some other value, or maybe it doesn't level off? So, so those are sort of things that, just to make it more interesting, I'll let you experiment with for the bonus. But that's basically a hint for where to go with that. You're just basically adding an outflow, which in the spreadsheet version would be adding another column. You could imagine putting it here, or maybe in between flow of water and tank gap that has an outflow, and then making sure to update your water level stock update formula so that it's the inflow minus the outflow, and that whole thing in parentheses times dt. And that'll allow you, just like in the bacterial case, to get this. Okay. So hopefully that's clear. Do we have any questions online or any questions from class? Feel pretty good about that. All right. Okay, so I showed you two very simple systems, and I hope you start seeing the similarity among the systems and some of the differences too. In all of these systems, we had these flows, and we had to, and really the big thing we're going to do in this class is come up with flow equations. And so you have to know like where there are like a few basic types of flow equations that we're going to have to get used to. And so a flow generically is going to be some amount of stock per unit time. So it's always going to be stock units divided by time units. So if our stock is in units of gallons, our flow might be in gallons per second. And so you can say, well, how do we conceptualize this? The flow is the instantaneous rate of change of the stock. What that means is if this rate of change were maintained for forever without any change, then in this time interval, the stock would increase or decrease by this amount. So if the rate of change was 5 meters per second, then we're saying that if the flow was held there constantly, if you waited a second, the water level would jump 5 meters. Now that doesn't actually happen because an instant later, the instantaneous flow might change from 5 meters per second to 3 meters per second. So that's why we have to simulate it, because it's constantly, we're sort of like the goalposts are constantly moving. And so we have to simulate it to see how the game plays out. But ideally in one snapshot, that's what the flow is communicating. At this instant, this is how things are changing. Okay, so like in the bacterial case, we had this inflow where we were saying that the bacteria here, each bacteria was oozing out new bacteria at a rate of 1 bacteria per W wait time. And because there were this many bacteria, the population was oozing out new bacteria at the number of bacteria times 1 divided by W. That's where we got that inflow. So another way to view that is if we waited for that W time and we assumed nothing else changed in the system, then each of the current bacteria would reproduce 1 other unit, and there would be that number of bacteria, more bacteria. So the idea here is if I waited, this flow is like how much is being added to the population. So if I waited the whole W time units and they kept oozing out at the same rate, then if I multiply this thing by W, then what I get is this many bacteria out. So they would double in that amount of time. Now, in reality, as they are pushing out new bacteria, those new bacteria are going to start pushing out their own new bacteria. So the instantaneous rate of change is going to change. So that's why we have to simulate it at every small time step to really capture not only the effect of the current bacteria, but the new bacteria being produced. So in this particular case, when we're talking about population growth rates, we form these flows by usually doing whatever the current number of bacteria is divided by the average time of reproduction. So if you ever have a growth model, be it like growth in a police force, for example, anything where the current number is going to encourage more of that. So whenever you have a positive feedback where, let's say the more students in a class, in a good class, that report that class is a good class on Rate My Professor or whatever, then the more students you get the next semester around. And so we can model the growth in students of the class with this sort of way, where it's the number of current students in the class divided by the average time it takes for them to leave a review and that review to be read and another student to sign up. And then that will give us an average rate of growth in the class. So in growth type models, this is the cookie cutter that we want to use for the flow. So that's what we did for kind of the bacterial case. Now you can also do that for death type models. And so the idea here, it's the exact same logic. If I had this L lifetime L, and each bacteria was popping out of existence at a rate of 1 bacteria per time L. And so all of the bacteria were contributing to the population getting smaller at a rate of the number of bacteria divided by the total life, or the average lifetime. And so if I waited for the average lifetime and the death rate stayed exactly the same, then after L time units, I would lose all of the bacteria. So that's kind of the idea there. Now, of course, that won't be the rate, because once I lose a few bacteria, then the death rate for the whole population is going to decrease because there's less bacteria available left over to die. And so that's why I don't get, after L time steps, they all die. I get this kind of asymptote where there's always a few long-living bacteria left in the population. So the idea here, it's the same logic. Whenever you have a decline, an exponential decline, where the decline is due to an individual living kind of, staying in the system for some average time, then this is how we model the average delay. So for example, at the end of class, some of you get right out the door. The rest, some of you hang around, you ask me questions, etc. If I wanted to model how quickly the room evacuates, then what I might do, or might ask Eric to do, is to take a stopwatch and measure how quickly each one of you leave the room. And then I could get an average for the average student in Ted's SOS 212 class leaves the room at whatever, 10 seconds. And from there, if I wanted to model that, then I could say, well, then what would the population look like over time? Well, I would say, well, if we had 30 students in the class, then I would model that with a little flow equation that would be the number of students in the class divided by 10 seconds. And if I initialize that stock with 30, then I would see this decline, kind of like the bacterial dying off, where I'd have immediately some popping quickly out the room, but then the ones left over would maybe take a little bit longer until eventually I get a population that, 1 or 2 that are hanging around for a long amount of time, and then eventually they head out too. So that's the way, whenever we have a decline that is generated by individuals leaving a system, we measure the average time they stay in the system, and the flow we use is the number of individuals currently in the system divided by that average time. That's how we write those flow equations. Okay, so that's for the bacterial inflows and outflows. So the general guidelines here for these population systems here is for stocks of individuals and population systems, measure the average time for the individual to be added to the stock. The inflow rate for each individual is 1 divided by that average. And so the contribution from all individuals is the total individuals times the individual rate, 1 over T. The outflow is roughly the same way. I measure the average time it takes for the individual to leave a system. The rate, the contribution of the outflow for each individual is 1 over that L. And then the total contribution for the whole population is the number of individuals times 1 over L. And that's how I form flows for population type systems. And I make sure that I choose my DT to be much smaller than all of these so-called, I'll call them time constants. So T or L or whatever, I want to make sure my DT is probably at least 10 times or 100 times smaller than the smallest one of these things as a starting point. So any questions about this for population-based systems before I flip to these sort of accumulation-based systems like the toilet? Remember, so as we move forward in the chapters, we are going to be just coming up with different ways to build flow equations. And these are very common types of flow equations we'll use. The other types of flow equations are like the toilet ones. So it seemed a little silly, bacteria model and toilet. I know bacteria grows on a toilet, but those two were not sort of picked arbitrarily. They actually model sort of 2 different classes of flow equations that we'll see over and over again throughout the semester. Okay, so in the toilet example, again, the way we interpret this is if that flow of water was maintained for a full 1 second, then all of the tank gap would be immediately filled. So that's the way this is kind of built here. So the flow water is tank gap divided by 1 second. So that initially is 15. So initially, if that flow stayed full tilt on, then in 1 second, you would go to the full tank gap, but then it would overflow soon after that. And so what's actually happening is this thing's slowing down over time. So the instantaneous rate is getting slower and slower and slower. And that's what causes this thing to not overflow. But that's the way we interpret this. At any instant, if you were to hold that valve fixed, then how quickly would, in 1 second, it would fill the rest of the numerator. That's the way we interpret that. So, and that's what I'm saying, but the valve is constantly changing. So actually the gap never gets quite to zero. So the guidelines for these types of systems is in bucket-like stocks that empty or fill and then stop. The inflow rate is always written as kind of a gap size divided by T. Now here's the weird part. T, this is how we get from data, is the average time it will take for 63.21% completion of closing the total gap. That seems like a weird number, right? 63.21%. It relates to the number e to the -1. I think I showed you that that curve, the toilet tank curve, was proportional to 1 minus e to the -t. And so this t here, this is what we call, it's frequently called a time constant. I think I've got that down here, a time constant, which has to do with the point. If we want to characterize, it's just a convenient parameter to characterize that curve, because that curve is this nonlinear curve. You know, it starts a little bit, it rises fast, and it slows down. And when you write it out mathematically, it's much easier to put in a constant t in there. You can do 1 minus e to the negative lowercase t divided by uppercase t. And you say, well, then what is that uppercase t that you're putting into the formula? Well, that's the time when it reaches 63% or 63.21% of the total rise. So it's just a funny little number there. But the idea here, it's still reasonable to do. You could, in figuring out the time constant for your toilet at home, you could flush it. And if you had like a little, laser, vibrometer, whatever, you could, in theory, you could watch the water level and you could take data on it and watch it go over time. And you could say, at what point did it reach 63% of the total tank height? And at the time where it hits that, that's what you put into Vensim as the time constant for your toilet model. So this is a way we go from data to models. For these tank type systems, we look for this funny little 63.21% rise time or time constant for the system. And then we choose our DT to be much smaller than this capital T. Again, 10, 100 times smaller. Okay. Now, for a normal toilet, does 1 second seem reasonable for the most toilets you reach there? Most, I think, toilets don't hit 63% of the tank height after a single second. That's pretty fast. So if you're to watch, if you've ever taken the lid off the back of the tank of a toilet, flushed it, the water kind of rises pretty slowly. It might take 4 or 5 seconds to hit that 63% mark. So that kind of, I used 1 second for convenience to keep the numbers, looking decent. But a real toilet, you probably would need to adjust. So instead of our flow being equal to the tank gap, for a real toilet, our flow should probably equal tank gap divided by 5 or tank gap divided by 4, because then that would slow down the toilet to match kind of the realistic timing for a real toilet. Okay, so those are the 2 types of systems that we work on. Any questions about that? So those are the 2 major types of flow expressions, the kind of individual population-based flows and these type of like bucket type accumulation-based flows. And as we start reading more of the Moorcroft chapters, we'll see real world systems that look like, more population-based or more bucket-like, or sometimes they're a different type of flow entirely, and we have to handle that on an individual basis. But a major slice of them will fit into one of these 2 areas. So any questions about the way these formulas came about? Okay. All right, so let's do a quick attendance exercise in the middle here, just to keep it honest, I guess. And the question I have here is, what is the special 2-word name we use for the for the T time, the 63.21% time in a bucket-like system being filled. So again, there's a two-word phrase that I say we commonly use for the time at which a bucket-like system reaches 63.21%. And I will sometimes use that term. So just want people to be familiar with that term. So let's just say, how many people, what is the term? Does anybody want to guess? Yeah. Time constant. So that's the term that I use to represent that 63.21% time. Okay. And those are graded for completion, not correctness. Yes. Oh, that's what. So what happens when you guys submit them double is it would be helpful for me if the next time you submit both answers so they're in the right spot. But if I see that like somebody only has one answer, I search down the spreadsheet to see if they submitted again, and I merge them manually. So it's easier for me if all your answers are in one, but if worst comes to worst, I do my best to try to combine them.
Okay, I can just like reload it and just start.
That's fine. That's fine. And if you're a duplicate, then it doesn't hurt things.
Okay.
All right. So we're moving toward Vensim. So we're moving out of the spreadsheet. So I'm not going to care that you guys know how to simulate things in spreadsheets for great detail. I want you to know that it can be done, but I really want you to focus on is how to build stock and flow diagrams and simulate them in tools built for that. So we've already talked about this. Stocks are the things that change in these systems. So a stock accumulates changes over time. All stocks together represent the state of a system. So a system is constantly moving to different states, and the things that are moving through those states are the stocks. So sometimes we use other terms like state variables, accumulators, levels, or these things called box variables, which just come from how they look in a stock and flow diagram. They have a box around them. So the typical symbol is a box. So this is what it looks like in Vensim. This is another program called AnyLogic. They draw stocks like this. This is what Stella draws stocks in, and this is what Insight Maker draws stocks. So there's significant differences here in how they look, but they all are drawn like boxes. That's kind of the common thing with stocks. The next thing is stocks can't change unless there's flows connected to them. So flows are the rate of change of or a component of the rate of change of the connected stocks. So they represent how a corresponding stock is continuously changing over time. Sometimes we'll use the term rate instead of flow, but they're identical. The typical symbol is a large, thick arrow, not the thin causal link arrows, but these large, thick arrows that typically have a little valve symbol in the middle of them. So here's what they look like in Vensim. Here, again, is what they look like in AnyLogic. This is what they look like in Stella, and this is what they look like in Insight Maker. So Insight Maker doesn't have the little valve, but it has this thick symbol here. And so sometimes they have this little cloud if they're not connected to a stock on that end. So you might have something that's an inflow to one stock, but we don't want to show that it might be getting the inflow from an unlimited supply. So going into one stock doesn't mean you're taking away from another. And then they'll put a little cloud to show that there's no limitations on the flow. But sometimes you can actually connect two stocks together so that as one stock is getting some inflow, then there's a corresponding equivalent outflow to the other stock. So that's kind of the symbols you'll see with flows. The other thing we've talked about are converters. Converters are just variables created to simplify calculations. So there's nothing special about them. They just make the formulas more readable, and they help expose more of the dynamics to the reader of the diagram, so they're not buried inside equations that aren't on the diagram. And so in Vensim, they look like circles around words. In AnyLogic, they're words above circles. In Stella, little circles as well. In Insight Maker, then they're ovals with words inside them. Sometimes there are these special cases where they might be a parameter, which means it's like an adjustable thing, like the toilet water level. And so some programs will have a little like indicator that you can change that parameter very easily. sometimes there's these things called table functions that we will talk more about as we get into this. And they're ways of taking an input and mapping it to an output without an equation, but instead by drawing a graph. And we've seen some examples of that in the fisheries models that were motivating the rest of the book back in chapter 1 of Moorcraft. And then finally, links. And so links just represent that there is an informational or causal connection between different variables. And so there's a dependency there. Sometimes we call them, there's a slight difference between causal links and informational links, but I'm not going to worry too much about the semantics of these. They're all links to me. And so we'll see this in a second here. I can't put a formula inside any of the other entities using a variable that is not linked to that variable. And so we'll see what we mean by this, but these give access from one variable to another of that information. Sometimes we annotate them as we do in a causal loop diagram. We'll put pluses and minuses indicating the direction. This is not necessary in a stock and flow diagram, but it can make the dynamical relationships more readable. So we usually don't penalize it, and I might ask you for it. I might say, draw a stock and flow diagram and annotate all the links, or show me the loops. So I might specifically ask you for it. In that case, give it to me. But in general, conventionally, stock and flow diagrams don't need these annotations. They're just put there to help the reader. Okay, so as an example of what I mean by this, let's consider a simple dynamical model, or what we're moving towards a dynamical model of a bank. And so in my bank, I've got a desired bank balance. I sure would like there to be a certain amount of money in my balances. I have all of my bank balances, and I have the gap between them. So these things kind of exist in isolation right now. If I were to go up inside this variable in Vensim, and I were to put this formula down here, gap between desired and actual, that's this thing, is equal to desired minus all. If I went to put that formula in there, if I just put the formula in there right now and hit play in Vensim, it would give me an error. And that error would be a legal formula. And that's because there are no links drawn in here. So this variable up here only gets access to other variables that are linked to it. So I have to first draw a link, and that will allow me to use desired bank balance up here. But I still can't use all bank balances because it's missing that link. So then I finally draw that link, and then Vensim tells me that that's a fine, that's a legal formula. It is a legal formula. So that is an okay formula because the links have given access to the information up here. So that's how I do that. So that's how links are used in stock and flow diagrams. Now, this isn't a dynamical model of a bank because I have no stocks. You can't have things change over time unless you have stocks. And so what I'm going to do is I'm going to put stocks into my model. And the two stocks that I'm going to use are the amount of money in my savings account and the amount of money in my checking account. So I can go up here, savings account balance and checking account balance, they're in boxes because they're stocks. And every stock, if it's changing over time, I'm going to either need an inflow or an outflow or both. And so I draw an inflow into my savings balance, and that's the interest. So I'm assuming that that's the only way the savings account balance is changing. And then my checking account balance, I'm going to have my salary. And given that I have a salary every 2 weeks, then I can model that pretty simply as a continuous flow. I take whatever my salary is every 2 weeks, I divide it by 2 weeks, and that gives me the flow for this salary. So, but I'm now still missing things. So, so like if I wanted to write all of the formulas here, I would need more links to make them work. So what links do you think I'm missing in this diagram? If we just look at the names of these variables, like desired bank balance, gap between desired and actual, all bank balances, savings account balance, and checking account balance. If I just look at the names of these things, what if I were to go in and imagine what formulas I would put in to the flows and to the other variables that were up here, then what links might I need to add in order to make those formulas legal? Yeah.
Like the current amount of money in the bank?
Yeah, right. So could you give me an example? You're on the right track. Give me an example of what link you would draw to sort of realize what you're saying.
Oh,
Any thoughts? Yeah. All bank balances. So you said connect maybe the balances here to these up here. Great, great. I think that's exactly what I was looking for there. So in order to calculate all bank balances, it's just a sum of my balances. Well, I can't sum up my balances unless I've released them to this variable to use. I do that by drawing these lines here. Now, in order for my savings account balance to calculate its interest, the interest flow needs access to the actual savings account balance. So that needs this link here as well. Now I can actually simulate this thing. I need to put my initial savings account balance. I need to fill in my salary, my interest rates, et cetera. The interest rate is baked inside this formula. My salary is baked inside this formula. I could break those things out to make them easier to change or something like that. But I could, in principle, simulate this thing. All of the right links are there. So any questions on this, on drawing links for this simple dynamical system of a bank? Questions online? Okay, yeah.
Okay, so why does the interest of the salary? Is it because like the salary is still being increased?
Right, so the question here is, I think if I can restate your question, why do I have this link for savings account, but no links down here? Is that right? Does anybody want to try to answer that? Yeah.
It's not because the interest affects the savings account balance, the savings account balance, then the interest affects the interest, but your salary, like the checking account has no effect on the salary.
Okay, how many people, so the answer there was, is that maybe because interest affects savings account balance and savings account balance affects future interest, but salary only affects checking, but not checking affects salary. How many people like that answer? Good, good, great. That's how I would answer it too. Question? Interesting question. So the question was, why don't the stocks need to be connected to desired bank balance too? Now, I might model a psychological effect where my desired bank balance would rise as my current bank balances rise. But here I'm modeling a simple model where I'm saying the only thing I care about is that I get whatever $1,000 in both my accounts. And if I just say that that's always my target, then that 1,000 doesn't depend on anything. It's just an exogenous parameter dumped into the system there. But there could be a feedback where you say, well, as I get closer to 1,000, then my desired bank balance is going to go to 10,000. As I get closer to 10,000, then it's going to jump to 20,000 or whatever. So I could do that, but this simple system, I'm just assuming it's constant. Great. Awesome questions. Any other questions here or online? All right, good. We're modeling. Excellent. Okay, so yeah, so questions there. Skip that one for now. All right, so we're drawing StockandFlow diagrams. Like I said, sometimes we annotate them to help expose causal structures that relate back to those system dynamics archetypes that we've seen back in the previous unit. So if I'm drawing an inflow to a stock, then I know that there is an implicit arrow that even though we don't draw this link, it's implicitly there. So whenever you draw an inflow into a stock, it is implied that there is a little link going down here, which says that as the inflow increases, the stock is going to increase. We often do not draw that, but it's always implied that it's there. So if you are analyzing these things as their little causal loop diagrams, you have to remember that that's always there. Similarly, and this is a tricky one, the outflow. So this stock outflow is going out. So we know that there's not necessarily a positive link between stock and outflow, but we might draw one. But we always have to remember that there always is a negative link from outflow into stock. In other words, as the outflow increases, the stock decreases. So we don't often draw this informational link or this causal link, but we have to remember it's always there. So when we're doing an analysis of where are the feedback loops, this is one that it's really easy to forget about because the flow arrow is going out. And so it doesn't feel like there's an arrow coming back. But you have to remember, because it is an outflow, there is an implicit arrow going back. Does that make sense? Okay, good. So combine those things together, and I've got them as kind of dashed lines here. For every stock, it has an inflow and an outflow. Whenever you draw this, you may not realize it, but you're effectively writing this mathematical expression. And whenever you draw this, you are implicitly drawing these causal links coming in here. And why that's important is because imagine if, like in the fisheries example, I have a stock of fish. Well, or I don't know if that's a fish because that would be reinforcing, but if I've got some system where I've got a stock where I have drawn a link back where I'm going to say the inflow to that stock depends upon the stock and the outflow to that stock also depends upon the stock, then I have to remember that there is a feedback loop here. Over here, sometimes it's usually easier to see this feedback loop because the inflow to the stock is just a positive link. But over here, it's really easy to forget that there's actually a feedback loop here. And the reason for that is, again, because of, well, I guess I thought I had a slide where I've got it, is because of those implicit links. So there is an implicit positive link here, and there is an implicit negative link here. And because this top link is negative, just because whatever this model, doesn't have to be negative, but the top link for this particular model is negative. And there is this negative coming back here. For this particular model, that's a reinforcing loop. Likewise, this model back here, because this link is positive going forward, and this in this model, whatever this model is, the link going backwards is minus, then it's a balancing loop there. So there are hidden feedback loops hidden in the flows. Any questions on that, where we got those? Yeah. Well, so the balancing, the B here is because of the two links together. This won't always be a balancing. So yeah, great question. Yeah.
Even though it's implicit, do you want us to make these stock groups?
Only if I explicitly ask you to, but I may ask you, it's more common for me to say label all the loops. And so when you label all the loops, then you should make sure that you don't miss these when you're labeling the loops. If you want to, for right now, put these in, that's fine. It just adds a little more kind of clutter to the system. It's not conventional to put those in. Most people would keep them out, but for now, I'm happy with you putting them in. Was that your question?
Yeah.
Okay, great. Okay, so so how do we add, what are the steps to adding these causal loops to StockandFlow diagrams? So we've got a StockandFlow diagram like this one. First we annotate the links with appropriate polarities. So that's already been done for us here. So we say that average time to reproduction to birth rate. Well, birth rate is 1 over average time to reproduction, so that's a minus. But birth rate's directly related to birth, so that's a plus. So I could go through and I could annotate each one of these, right? After you do that, then I have to remember, and this is either in your head or explicitly, I've got positive links for every inflow, and I've got negative links for every outflow. So then after I've done that, then I can go through and annotate my loops. And so now I can find all the loops because I've explicitly put those in, or I've remembered that they're there in my head, and then I can label my loops properly. And then I can usually omit the links that I added because my audience is more interested in these things, and these extra loops down here are going to be confusing. So usually your stakeholders, you get rid of that stuff, but it's okay intermediately to add them in. Okay. Now, fortunately, in Vensim, there's actually a tool that allows you to find all the loops. and it knows that these implicit loops are there, and so it'll find these things for you so that you don't have to manually be doing it if you want to use that tool. Okay, so so like in this particular case here, I want to say like, well, what is the polarity here? Well, so we have to first say like, well, is this a loop? Well, this is a loop because there is an implicit positive link from flow of water to water level because it's an inflow. So there's a negative link to tank gap, a positive link to flow, a positive link to flow to water level, which is exactly this balancing diagram that I think I asked you to draw in assignment D2 even, so right here. So I have to remember that that's there implicitly, and by remembering that's there, I can see there's only one negative link in this loop, and it's a balancing loop. All right, so any questions about this simple diagram and how we got balancing there and how we ended up turning this loop into that loop? This funny little figure 8 thing is just my way of trying to highlight that there's a hidden link there. So that's not any special annotation or anything. Okay. All right, good. Questions online? Now I want to do a demo in Vensim and a demo in Insight Meter. Okay, so I'm going to bring up Vensim on my machine here. I'll do this live. And hopefully this goes well. All right, so if you were to open Vensim, which you can do if you'd like, I am going to first, for my system, increase the font size here, which I just did. You didn't see me do it, but I just did there. And so I'd like to draw a stock and flow diagram. Maybe I'd like to draw that bacteria diagram. So it's not that much different than the causal loops. We just make use of some things that we haven't used before. So I can, now there's this new level that I've clicked on up there. And if I click anywhere, I can now type bacteria, and it will draw this level there that if I want to, I can make a little bit bigger by dragging that handle, and there it is, getting bigger here. So that's my one stock. I could have multiple stocks, but for this system, I've got this one stock. Now I need to draw inflows into that stock because the stocks change. And so I'm going to go up here to what is labeled rate. And if I click on that guy, then I can click where I want the rate to start. And I'm not dragging, it's waiting for me to click a second time. See, not dragging. Then I can just click on bacteria and it will draw that flow. And then I can type in whatever I want to call that flow. So I could call this births or even population birth rate. Maybe that's more accurate because it's a rate. Pop birth rate. Let me see here. I'm going to drag this. Because of my font size, I think it sort of compressed it into one. So I'm just going to drag it over here and fix that, which should hopefully be easier for you guys. Pop birth rate. There we go. So I'll drag this back. All right, so now I need my outflow. Yeah.
I didn't see how you got the
Different
different tools.
tools? You mean the level up here?
Yeah, how do you? Yeah, I don't have them either.
So it may not say, depending on if you have the I forget if I'm in new sketch or old sketch right now, but can I just peek around to see what you're looking at there? Right, okay, so if you have the new sketch, it may not say the words down here. So, but you should see a box and it'll say S, I think, in the middle of it. Or maybe it'll say, can I look at see? Yeah, S, that's what you want. So if you're using the new sketch tool, I'm sorry, this is the old sketch tool, level is a box with an S in it for stock. Variable still is a box or says A in it. And then under rate, mind if I look at yours again? Sorry about that. And under rate, it's kind of a thick, it's that one there. Yeah, it's, the rate tool kind of looks like 2 bars with an arrow in between it. And so but once you've clicked on them, they should act exactly like this. So if I go to that rate tool again, and by the way, if I also have a tutorial online that's probably better quality than this one, that I called pop death rate. So I've got these 2 things, my birth rate and my death rate. I know that I'm going to need a variable. So on the new sketch tool, it'll just say A there. And so I'm going to create a variable called, I'll call it indiv birth rate. And I can say indiv death rate. And I know that my birth rate is just 1 over the average lifetime. So I can create an average lifetime. I'm sorry, that's average lifetime is supposed to be average time to reproduction. And then over here, I have average lifetime. So these are all the variables that I think I'm going to need in my model. So now I need to draw my causal links, just like in a causal link diagram or causal loop diagram. So I go now to, in the old tool where it says arrow, in the new tool, it'll just have a single little line as the icon and a little curve to it. And now I can just link things up. So I know that in order to calculate individual birth rate, I need to connect average time to reproduction to individual birth rate because the formula is going to be 1 divided by that. I'm then also going to need to connect individual birth rate to population birth rate, and we'll see how that works. I'm going to need to connect the number of bacteria to the population birth rate, and I can grab this little handle, or I can try to grab this little handle. There we go, and drag it up. Then I can do the same thing, bacteria to population death rate, because those depend on each other. Individual death rate is going to go to population death rate. Well, that's what happens when you accidentally double have it go around. And then average lifetime to individual death rate. So those are all of the causal links that I'll need to make the formulas work. So this doesn't look that different than how we drew a causal loop diagram. So now I need to actually put the formulas in play. And so the formulas here, there's an f of x here. In the old sketch, it actually says equations. I think in the new sketch, it's roughly over in this position, but it still says f of x. It just may not have a word underneath it. And if I click on that, it will highlight with a black background all of the things that need equations that don't have the equations already put in there. So I could start with my stock. The stock is one of these ones where I don't put a formula in, I put an initial condition. So if I click on the stock, it gives me this thing here where it's already filled in a lot of important stuff. And the only thing I care about with every stock is the initial value. So that's the thing down here, initial value. It's just this box. You don't put any formulas in the initial value. You just put a constant. And so I know that I initially only need 1 bacteria in my system. So I fill that in as 1. So then I'm done with that one. So I can say, okay. And then if I now can go to say, average time to reproduction. So I click on that, and this is not a formula, but it's just a constant. I know that we said our average time to reproduction was 0.75. So I'm going to put 0.75 in here. And then I'm going to hit OK. And then I'm going to go down to individual birth rate. And now the individual birth rate here, this is where things get more interesting. I want that to be 1 divided by the average time to reproduction. So if I look down here in this little box, this shows me all of the variables that I have access to because they've been linked to this variable. So I can do 1 divided by and then click on average time to reproduction or just manually type it. So I can do 1 divided by, and then I can just click on this thing and it fills that in. And that formula is done. It's a little small, but it says 1 divided by average time to reproduction. So I'll click OK there. And I promise we will get to the sim, and then I might continue this the start of next time. Like I said, there is a full tutorial that's a little cleaner than this. For population birth rate, this is just the number of current bacteria times the individual birth rate. Well, because I've drawn those causal links in, those are both available for me down here. So I can just do bacteria times individual birth rate, just like we did in the flow columns of your spreadsheet. So then kind of moving quickly through here, I'm going to do the exact same thing with these 3. I'm going to put in 3 time units here, 1 divided by that here, and then bacteria times that here. So I'll go up here and I'll do 3. I'll do individual birth rate is going to be 1 divided by average lifetime. And then population death rate is going to be bacteria times individual death rate. And the final thing I need to do before I can actually simulate this thing is go up to model and go to settings. And it asks me here if I want to save, which I can do, but I'm going to skip that for now. And this is where the DT is located. So it tells me how long do you want to simulate this thing? 5 time units. And what do you want your time step to be? That's your DT. And I'll give you the last attendance question in just a second. And I'm going to put 0.01 there. And if I do all of that, then I can go up and hit play. It'll ask me again if I want to save. It'll say that it might tell me the data set currently exists. I'm going to say yes, I want to overwrite it. And nothing appears to happen, but it generated data. And if I go over to graph, I can click, say, on bacteria, highlight it, and then click on graph. And it brings up a graph like this one, which looks exactly like I expected. And if I go to table, then it actually generates a table. If I click on actually table down, it'll be a table that'll look more like we were expecting. And this is exactly the table of values we got out of the spreadsheet. So that's an example where we've drawn a diagram and it's effectively built a spreadsheet model for us with this DT, and we're done. So I will touch on this again, the start of Thursday's lecture, and I'll also show you Insight Maker. You can also watch separate tutorials that I've linked on Canvas for both Vensim and Insight Maker. So, so the only other things that, let me get out of Vensim here or back into PowerPoint. All right, so I'll show you Insight Maker next time. Quick announcements, reading due on Thursday. You know about the exam stuff. There is a new assignment where you're going to build the toilet model using Vensim or Insight Maker, and that'll be due Sunday. This is your cheat sheet for that assignment. So you're basically doing everything here, like I've kind of shown you all that you'll need to implement inside Vensim. You're sort of copying this. And that's all I've got for you today. So let's give you a last attendance exercise. And sorry for the rush here at the end. Like I said, we'll touch on things next time. And the question here I have is, what is the initial condition used for the toilet water level stock? So what initial condition did we put into the stock for the toilet water level? It was a number. So what number did we use for the initial water level in the toilet example? And that's all I've got for you. So if you have any other questions, you can feel free to come up with me after here. And otherwise, I'll see you Thursday. Mhm.
So for the total on the extra credit, does that look right? I did the leap is 0.1, my DT is 0.1, and it's 0.1, like it's 1 every second, so I divide by 0.1 seconds.
Oh, well, so you don't have to worry about the DT. So the leak is just going to be the value that I gave you. It'll be 1.
Right.
So it wouldn't be 0.1.
But since this goes by like 0.1 seconds, like it would be going what? It would be like, because I subtracted it, so it'd be going down by 0.1 every 0.1 seconds.
Well, you remember, so that extra math is done for you in the magic of the water. So if you look at your stock, so like look at your water level, like show me a formula for your water level, like where like go to 1.5. So if you change that C7 to be a parentheses inflow minus outflow. So like if you were to create a column called outflow, or actually you could use delete. So you could make that C7, you could print these around it, you could say C7 minus $B $3.
Okay.
And if you just put that in there, because it's multiplied by DT, it does all that extra math for you.
Okay, so this one is wrong right here.
Right, it's, yeah, this one is not quite right.
Okay, so then I would just be changing my water level minusing the leak?
You would, so right now you only have an inflow.
Yeah.
So you need an inflow minus outflow. The outflow is constant, it's always equal to 1.
Okay.
So you just change that C7 to be parentheses C7 minus 1, and that whole quantity, C7 minus 1 times the DT.
Okay, thank you.
Okay.
Could I pet the puppy or?
If there's any questions online, you can feel free to let me know or put them in the chat. Otherwise, I'll be closing the room shortly. Yeah, you have a question?
I'm trying to make something that's graph.
Okay.
It doesn't seem very.
So that, what can I take a look at your average lifetime? Yeah, look at the formula for it. So click on, yeah, there you go. 3, okay, and then there's actually a shortcut here. So if you click to individual death rate, 1 divided by average lifetime, okay, and then look at the population. So if you scroll down a little bit in this little box here, yeah, look at pop death rate, bacteria times individual death, all that looks good. So now scroll up and show me average lifetime. Change that to 0.75.
Okay.
It happens always. If you hit OK there, I bet now, well, not completely sure, but now you have to rerun the sim. So go ahead and simulate. It'll say, do you want me to overwrite? Say yes. And then click on bacteria and then click on graph. And so it's still declining quickly. So let's look at your, I think it might actually be that this rate, like, so if you look at the formula for bacteria, so click on the equation and then bacteria. Yeah, okay, so somehow it deleted that flow. So what I do is hit cancel there and just go ahead and delete. So go to your delete and just delete pop birth rate and just redraw it and delete the little cloud guy too. So that rate, yeah, good. Right. And then you'll need to redraw the arrow. Good. And then redraw it from bacteria back. And then you have to update that formula. So it'll just be bacteria times individual birth rate. And then hit OK there. And then it wants you to double check this one because it's saying, I updated this because you drew a new flow. So let's go ahead and take a look. So that's correct. And then you see now it has the inflow minus the outflow. So, so if you click OK there, rerun your sim. And then you can hit bacteria and hit graph, and it'll graph the bacteria. And so right now it's showing it constant, which indicates to me that somehow, let's hit close there. Let's look at your average time to reproduction and make sure it didn't somehow get changed back to 3. It's 0.75. So then, right, so now it's individual birth rate. Let's look at that. And then average time to reproduction. Oh, right, and then, I'm sorry, and then look at population birth rate. Let's look at that. And then let's look at pop death rate. Oh, hi, pop. Oh, wait, no, sorry, go to that pop death rate. Okay, and then let's look at individual death rates. Just for some reason, oh, you know what? I bet I know exactly what it is. So click OK. And then go to model settings.
Oh, yeah.
And your time step looks good. Change your final time to 5, I guess. Okay. Let's try simulating that. So hit simulate, say yes. Click bacteria and click graph. And it's still holding constant as if the death rate is not. Yeah, it's like your inflow and your outflow are equal right now, and it's holding that one constant. I don't see. Bacteria times into death. And that says constant, which is good.
Oh, wait. Yeah, my average lifetime, my average.
Oh yeah, so that average average time to reproduction, we want to be 0.75. Average lifetime, 3. So now I bet if you rerun it, regraph it, then you'll get an exponential growth curve instead of that decay. There it goes.
Okay.
Does that kind of make sense?
Yeah,
like,
yeah.
Okay.
Yeah, no, that makes sense now.
Yeah. So it's doing exactly what you expected if the birth rate and death rate were equivalent.
Right. Okay.
I'll go ahead and end here.
Dr. Pavlic.
Hold on a second. I just yeah, like,
By all means.
okay. So I'm going to just stop recording, but I'll leave.